Next content in my module, light and hydrogen spectra. Light we do in chemistry, you also do quite a bit in physics. And then hydrogen spectra, I talk about the concepts, but then I also do calculations here. For the A-level, most A-level boards, you don't have to do those calculations. But I find that for some people, it can actually help to reinforce the ideas and show them the concepts at work. So I include that, even though A-level doesn't. Start off though with light. The arrangement electromagnetic radiation starts with lowest energy and increases to the greatest photon energy. And we have all these wonderful words here, radio, visible, blah, 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 blah. Now, of course, you might recall that in my slides, I had this beautiful slide here that shows you all of the frequency. So frequency going from right to left as it increases. So radio waves going all the way up to gamma waves, red going all the way up to purple, and then wavelength, of course, goes the other direction. So as we go in this direction here, you'll see we're going from 10 to the 8 down to 10 to the minus 16. So wavelength decreases as we go in this way. So radio waves, longest wavelength as we go down. Red has the longest wavelength of the visible spectrum. So let's pull out and summarize the important little bits of this right there. So as I read this from left to right, the wavelength is increasing. So gamma rays, smallest wavelength, radio waves, largest wavelength. And similarly, therefore, if I read it back from right to left, my energy and my frequency are increasing. So radio, lowest energy and frequency, gamma, higher energy and frequency. Now I need to make a quick pause here, if you haven't been watching some of the videos, and point out that the symbol that I'm using here for frequency is not F, as you find in A-levels, but it is nu. Go outside of the UK, and more often than not, people are going to use the symbol nu for frequency. Thus, if you had never seen it before, you would freak out, you would wonder what this funny distorted V is, and so forth. And this is a trend I'm going to use all the way through my modules and movies. I want you to be familiar with the units that are used outside the United Kingdom, as well as, of course, the units that you need for A-level. I want you to be familiar with different symbols, and later on when we get into particularly organic chemistry, I want you to be used to different naming conventions. There's no point when you go out into the big wide world of science in being totally blinkered as to the way that A-level presents things. So in this set of movies, I'm going to use nu for the frequency, and then when I get into the A-level worksheet, I'll be using F for the frequency. It's not intended to confuse you, it is intended to expand your education. Anyway, this is the little set of data that we're going to use for quite a few questions. This particular question here, select the arrangement which starts with the lowest energy and goes to the highest energy. So in other words, what we want to do is see which of these reads as we go from right to left. Okay, going from right to left, the energy is increasing, so we'll start with the lowest energy here and read through to get to the highest energy here. I'm going to do this one slowly, and in future questions I'm going to speed up a little bit. So we got radio, that's great, then visible, that's great, then infrared, no, infrared is out of order. Next one, microwave, great, infrared, great, visible, great, ultraviolet, great, excellent. Okay, that one looks pretty good. Moving to C, we go visible, ultraviolet, infrared again, messing up, then gamma rays. D, we go X-ray, video, infrared, microwave. That's actually flipped, isn't it? The wrong direction. And then this one here, microwave, that looks good. Ultraviolet, that looks good. But again, infrared, out of place. So therefore, the only one that correctly starts at the lowest energy of the ones listed, microwave, then infrared, then visible, then ultraviolet, is B. Okay. Which of these types of radiation in order of increasing wavelength. So we want increasing wavelength. So now we want to read from left to right. So visible ultraviolet X-ray, visible ultraviolet X-ray. No, that one's flipped. Radio, visible ultraviolet, radio, visible ultraviolet, again flipped. Ultraviolet, visible infrared. Oh, there we are reading from left to right. So that looks pretty good. X-ray, visible, ultraviolet, X-ray, great, visible, yes, ultraviolet, out of order. But then we decided can't be none of these because we did like C that went ultraviolet, visible, infrared. So that looks like the answer. Notice again that even though when I think I've found the answer, I keep reading just to make absolutely sure that there's not something that looks equally as good, if not better. Always, always, always look at all the answers in a multiple choice question. Following is false, so less energy for the first one. Well, energy, of course, we're going from right to left as we increase. Infrared right there, red right there. Infrared has less energy than red because it's closer towards the lower energy lot, so that one looks pretty good. Violet has a longer wavelength than ultraviolet. Well, wavelength, we're going from left to right. There's violet, there's ultraviolet. Violet has the longer wavelength because it's on this side, right? Wavelength in our little series increasing as we go from left to right, so that's good. Gamma rays have the highest frequency. Well, highest frequency is down here. Gamma looks pretty good. X-rays right there, longer wavelength than ultraviolet. No, that's the wrong way round, isn't it? Wavelength increasing this way, so that means that ultraviolet will have a longer wavelength than X-ray. And finally, green light, more energetic than yellow. Well, there's green, there's yellow, energy going up from right to left, so green has a higher energy than yellow, so that looks correct. Again, checking all the possible answers. Now we'll move into some calculations, and to do these we're always going to use these two relationships. C, speed of light, is wavelength times frequency, and energy of a photon of light is h times the frequency. So let's see what we got here. What is the wavelength that has an energy, given that C and H, so given you C and H. So we know the energy. From the energy we can get therefore the frequency. Pop in our values, 3.2 times 10 to the 20 into there. H, 6.6 times 10 to the minus 34. Frequency, we don't know. We're going to calculate that here. So the frequency, 3.2 times 10 to the minus 20, divided by, bringing that over down here. So divided by 6.6 times 10 to the minus 34. And the frequency, 4.84 times 10 to the 13. And the units of frequency are per second or hertz. Because we didn't want the frequency, we wanted the wavelength. Well, that's all right, because once we have the frequency, we can use this relationship here to give us the wavelength. C, 3 times 10 to the 8 meters per second. Lambda we don't know. Frequency we've just worked out, 4.84 times 10 to the 13 per second. Pop all that in, and we get the lambda is 6.2 times 10 to the minus 6 meters. Now, as we look at our possible answers, we got 6.2 minus 7, 6.2 minus 5, 6,200, and then some ones that are obviously nothing to do with it. Okay, well, which of those is it? And this is where we need to know our metric prefixes. 6.2 times 10 to the minus 6 meters. We want that in nanometers, presumably, just to check that this one is correct. So the way I do the units is I'll take what I've got and I'll multiply it by something that gets rid of what I've got, so cancelling out meters with meters there, and replaces it by what I would like. So in this case, that's nanometers. And a relationship that we know is that 1 nanometer is 10 to the minus 9 meters. So put all that through, punch it into your calculator, and we find that 6.2 times 10 to the minus 6 meters is 6,200 nanometers. Same type of question, except here I've given you the wavelength, 550 nanometers, and asked you for the energy. Well, again, we're going to use these same relationships. C is lambda times nu, and E is H times nu. Green light, frequency of 550, so we know the frequency, as we know the wavelength, so we can therefore get the frequency using this relationship. Punch everything in, 3 times 10 to minus 8, 550 nanometers times the frequency. Well, the trouble here, that my speed of light is in meters, but my wavelength is in nanometers, so I either have to convert this to nanometers or convert this to meters. Much easier to convert this to meters, knowing that, of course, nano means 10 to the minus 9. So pop that in, 550 times 10 to the minus 9. That replaces the nano, so that leaves me with meters. Rearrange that, and we get the frequency, 5.45 times 10 to the 14 per second. Now I've got that, I can get the energy. E is H times the frequency. Pop everything in. H, of course, 6.6 times 10 to the minus 34 joules seconds. Frequency, we've just calculated 5.45 times 10 to the 14 per second. And that gives me that the energy of a photon, 3.61 times 10 to the minus 19 joules. Very important, and you'll see this when we get into the actual A-level questions. You look at the units for this. This equation here gives us the energy of a photon in joules, and a very small number of joules. A lot of times you're not going to worry about the energy of one photon. You'll worry about the energy of a mole of photons. So always look to see, are you talking about a photon or a mole of photons? And more examples of that, as I said, in the A-level question work through movies.